It is the 4th of March, 1943, and a hut on the western shore of Patricia Lake, deep in the Canadian Rockies, is filled with the smell of sawdust and the low hum of a refrigeration plant working through the night. Outside, the temperature has dropped below -20, and the lake itself is locked under a meter of ice. Inside, a small team of engineers and laborers from the National Research Council of Canada are pouring a strange gray slurry into wooden molds, layer after layer, while pipes carrying brine snake along the walls to keep the mixture from melting before it sets. What they are building looks at first glance like nothing more than an oversized ice rink shed. It is not. It is the test hull of a ship that, if its sponsors in London have their way, will weigh 1.5 million tons, stretch longer than 2.5 football pitches end to end, and be made almost entirely from frozen water and wood pulp. The British government has decided, in the depths of the most desperate naval crisis of the war, that the answer to Hitler's submarines might not be steel at all. It might be ice. This is the story of Project Habakkuk and of pykrete, the strange composite material at its heart, an idea so unlikely that it sounds, even now, like something dreamed up for a children's adventure story. And yet it was taken seriously by the Admiralty, championed personally by Winston Churchill, and developed with real money, real scientists, and a real prototype that still lies, intact, at the bottom of a Canadian lake today. Understanding why Britain came so close to building a frozen aircraft carrier tells you something important about just how close the Allies came to losing the Battle of the Atlantic, and how far desperate men were willing to go to close the gap. By the winter of 1942 and into early 1943, Britain's supply lines across the Atlantic were being torn apart. German U-boats, hunting in coordinated wolf packs, were sinking merchant shipping faster than British and American yards could replace it. In a single month, November 1942, more than 700,000 tons of Allied shipping went to the bottom of the ocean. The figures were not abstract. Each sunken tanker meant less fuel for Britain's war machine. Each sunken freighter meant less food on British tables, fewer tanks reaching North Africa, fewer aircraft parts crossing from American factories to British airfields. Convoys crossing the mid-Atlantic faced a corridor of several hundred miles, sometimes referred to bitterly by sailors as the Black Pit, that lay beyond the range of land-based aircraft from either Newfoundland or Iceland. Within that gap, U-boats could surface, recharge their batteries, and attack with comparative impunity, because no aircraft could reach far enough out to sea to hunt them down or to drive them under. The obvious solution was air cover delivered from escort carriers, but here Britain ran into hard limits of industrial capacity. Building a conventional aircraft carrier required enormous quantities of steel plate, skilled shipyard labor, and months, often years, of construction time at facilities that were already overstretched building destroyers, corvettes, and merchant tonnage to replace what the U-boats were destroying. Steel itself was rationed and fought over by every branch of the armed forces, with the Air Ministry, the Army, and the Admiralty all competing for the same limited rolling mills and the same limited pool of skilled riveters and welders. Even if the political will existed to divert resources to dozens of new carriers, the industrial capacity simply did not exist alongside everything else Britain was being asked to build that year. Some naval planners calculated that closing the air gap with conventional ships alone might require diverting steel and labor on a scale that would cripple other parts of the war effort for years, perhaps delaying landing craft production for any future invasion of occupied Europe, or slowing the replacement of merchant tonnage already being lost faster than it could be built. There was also a more basic vulnerability to consider. A conventional steel carrier, however well armored, remained a single point of catastrophic failure. One well-placed torpedo, one bomb finding its way past the anti-aircraft screen, and months of construction and an entire crew complement could be lost in minutes, a risk made starkly real by the loss of British and American carriers earlier in the war. The problem, in short, appeared to have no solution within the constraints of existing materials, existing shipyards, and existing vulnerabilities. It was precisely the kind of impossible problem that attracted Geoffrey Pike. Pike was not a naval architect nor a conventional military man at all. He was a journalist, an inventor, and, by most accounts, an eccentric of the first order, working at this point for Combined Operations Headquarters under Admiral Lord Louis Mountbatten, a body set up specifically to pursue unconventional approaches to the war that more traditional service branches might dismiss. Pike's proposal, submitted in 1942, was audacious even by the standards of an organization built to entertain audacious ideas. If steel was the bottleneck, why not build a vessel from a material that required almost no steel at all, that could be manufactured using labor and machinery already familiar to the pulp and paper industry, and that could, in principle, be produced in quantities limited only by access to cold water and wood fiber? His answer was a composite of ice and sawdust, later refined and tested rigorously enough to earn its own name, pykrete, after its champion. The science behind pykrete was developed properly at the Combined Operations Research Establishment, with crucial laboratory work carried out by a young Austrian-born crystallographer named Max Perutz, working initially in a meat locker at Smithfield Market in London, of all places, because it was one of the few facilities in wartime Britain that could reliably hold sub-zero temperatures. Perutz discovered that mixing roughly 14% wood pulp into water before freezing it produced a material with startlingly different properties from ordinary ice. Pure ice is brittle. Struck hard enough, it shatters, and under sustained stress it slowly deforms and cracks. Pykrete, by contrast, behaved almost like a weak concrete. The wood fibers bound through the ice matrix, distributing stress and resisting fracture in a way that pure ice never could. In demonstrations, blocks of pykrete could absorb the impact of a rifle round without shattering, where equivalent blocks of plain ice would burst apart. It also melted far more slowly than ordinary ice, a critical property if a vessel built from the stuff was expected to survive an Atlantic summer. There is a frequently repeated story, impossible to verify with full certainty but consistent with contemporary accounts, that Pike demonstrated pykrete's resilience to skeptical senior officers at the Quebec Conference in 1943 by firing a pistol at a block of it and a block of ordinary ice side by side, with the ordinary ice shattering while the pykrete merely absorbed the round, the bullet reportedly ricocheting and narrowly missing one of the assembled admirals. True or embellished, the anecdote captures why the material captured the imagination of people who would otherwise have laughed the proposal out of the room. Beyond its resistance to impact, pykrete had other properties that made it attractive to naval planners working under wartime constraints. Producing it required none of the specialized alloys, none of the precision machine tooling, and almost none of the skilled welding labor that a steel hull demanded. In principle, the raw materials, water and wood pulp, were abundant and cheap, and the manufacturing process bore more resemblance to operating a paper mill than to running a shipyard, meaning that labor could be drawn from industries that were not already stretched thin by other war production. Engineers calculated that a vessel of the proposed scale might require roughly a quarter of the steel of a conventional ship of similar displacement, with that steel reserved largely for the refrigeration piping, propulsion machinery, and reinforcing mesh embedded within the ice itself, rather than for the hull structure that would otherwise have consumed the bulk of it. The vessel imagined around this material was staggering in scale. Project Habakkuk, named after a biblical verse about a work being done in your days that you would not believe even if you were told, envisioned a floating air base some 600 meters in length, displacing around 1.5 million tons when fully fitted out, dwarfing every other warship then in existence by a considerable margin, more than 20 times the displacement of a typical fleet carrier of the period. Its hull walls were to be more than 12 meters thick in places, thick enough that conventional torpedoes and aerial bombs were expected to do little more than gouge craters that could be repaired by simply pouring and refreezing more pykrete slurry over the damage, a self-healing quality no steel hull could match. Refrigeration plants embedded throughout the structure, similar in principle to a vast network of household freezers working in concert, would keep the hull solid even as the outer layers slowly melted or absorbed battle damage. Designers envisaged roughly 26 electric motors driving the vessel, an unusual propulsion arrangement made necessary by the unconventional hull material, since traditional shaft arrangements running through a frozen structure presented engineering problems nobody had previously had cause to solve. Aircraft would operate from a flight deck on top, while the enormous internal volume housed workshops, magazines, fuel stores, and crew quarters carved directly into the frozen structure, an idea that sounds more like submarine engineering scaled up to absurdity than conventional shipbuilding. To test the concept at a workable scale before committing to the full design, the Canadian government agreed to host a prototype. Built at Patricia Lake in Jasper National Park, chosen for its isolation, reliable winter cold, and distance from prying eyes. Laborers, many of them conscientious objectors assigned to alternative service, worked through the winter of 1942 into 1943 to construct a scaled-down test hull roughly 18 meters long, insulated with wood shavings and sawdust packed around a wooden frame, and kept frozen by a small onboard refrigeration unit. It was, in effect, a working model 1/40th the length of the proposed full vessel, built to test whether pykrete could be manufactured, maintained, and kept structurally sound over an extended period under field conditions rather than in a laboratory freezer. If you are finding this interesting, a quick subscribe helps more than you know, and there is more of this story still to come. The prototype at Patricia Lake did, broadly, work. It held its shape through the test period. The refrigeration plant kept the core sufficiently solid even as ambient temperatures fluctuated, and engineers gathered useful data on melt rates, structural behavior under load, and the practical challenges of working with a material that needed to be poured, frozen, and shaped almost like ready-mixed concrete, except that concrete does not require keeping below freezing for months, at a stretch using power-hungry refrigeration equipment that itself needed fuel, maintenance, and skilled operators in numbers that began to trouble planners back in London. Workers found that maintaining the structure required near-constant vigilance, with crews monitoring brine temperatures around the clock and patching small areas of surface melt before they could spread. The labor, drawn substantially from men assigned to alternative wartime service, worked through a genuinely harsh Canadian winter, and surviving accounts describe a strange, almost surreal atmosphere around the lake, an isolated construction site shrouded in secrecy, where local residents were told only that some manner of unusual engineering work was underway and were firmly discouraged from asking further questions. There is, in truth, very little operational history to recount beyond the prototype, because Project Habakkuk in its full form was never built. No squadron ever flew from a deck of compacted ice and sawdust. No German U-boat ever had to contend with a frozen airbase appearing on the horizon. This sets it apart from most weapons covered in stories like this one, where the drama comes from combat itself. Here, the drama lies entirely in the scale of ambition and the speed with which reality eventually caught up with it. It is worth being honest, too, about the limits of what can be claimed with confidence. Much of the surviving documentation on Habakkuk was generated by a small circle of scientists and officers working under wartime secrecy, and some of the more granular engineering figures, exact propulsion arrangements, precise projected costs, and detailed timelines for full construction, were never finalized before the project was wound down, meaning historians today are often working from preliminary studies and committee minutes rather than a completed design. Compared with German efforts of the period, there is simply no equivalent program to point to. German naval planners were, if anything, retreating from large surface combatants by this stage of the war, focused instead on submarine production and smaller, faster vessels, having largely abandoned ambitions for new capital ships after early war losses and Allied air superiority made such projects increasingly suicidal. Germany did experiment with various unconventional materials and improvised construction techniques as raw material shortages worsened later in the war, but nothing approaching the scale or ambition of a composite ice capital ship ever appeared in German naval planning, and no comparable proposal survives in German wartime records. The Americans, facing the same mid-Atlantic air gap problem, pursued a far more conventional and ultimately far more successful solution, mass-producing small escort carriers on merchant hulls, the Bogue and Casablanca classes among them. Built from steel in established yards using assembly line techniques borrowed from civilian shipbuilding. Dozens of these vessels entered service through 1943, providing exactly the air cover the Atlantic Gap demanded, at a fraction of the engineering risk and uncertainty that Habakkuk represented, and at a pace measured in months rather than the years a full-scale ice carrier would likely have required. Where Habakkuk promised a single, enormous, largely untested vessel, the American approach delivered dozens of smaller, proven ships built on a hull design already familiar to American shipyards, a difference in philosophy as much as in material. In the end, it was this unglamorous, conventional solution, not the frozen Leviathan from combined operations, that helped close the gap and turn the tide against the U-boats by the middle of 1943. What ultimately killed Project Habakkuk was not failure of the science, but the changing shape of the war itself. Improvements in long-range aircraft, particularly the extended-range Liberator bombers that could finally cover the Black Pit from existing land bases, alongside the introduction of escort carriers built conventionally and at speed, closed the air gap by mid-1943 without any need for an ice-built airbase that would have taken many more months and consumed enormous quantities of refrigeration equipment, steel piping, and skilled labor that Britain could ill afford to commit. The calculations that had once made pykrete look like a clever workaround for a steel shortage began to look, on closer inspection, like a project that would consume nearly as much steel in refrigeration machinery and structural reinforcement as it was meant to save. By late 1943, with the immediate crisis easing, the project was quietly allowed to lapse rather than formally canceled with any great drama. The legacy of Habakkuk is curious precisely because it left almost no military legacy at all, and yet it left a real scientific one. Max Perutz, who had spent those cold months studying ice crystal structures in a meat locker, went on to apply techniques developed during this period to the study of hemoglobin and protein crystallography, work that eventually earned him a share of the Nobel Prize in Chemistry in 1962, a remarkable second act for research that began as wartime improvisation. Pykrete itself occasionally resurfaces in engineering curiosities and survival demonstrations even today, a reminder that the underlying material science was genuinely sound, even if the vessel built around it was not destined for service. As for the physical prototype, it was deliberately scuttled in Patricia Lake once testing concluded, and divers can still visit its remains today, the wooden frame and insulation still largely intact in the cold, oxygen-poor water, a strange and little-known underwater monument to one of the war's more imaginative dead ends. It is worth being honest about what is documented and what remains uncertain in this story. The broad outline, the air gap crisis, Pike's proposal, Perutz's laboratory work, the Quebec Conference demonstration, and the Patricia Lake prototype all rest on solid documentary and physical evidence, including the wreck itself and surviving combined operations records. Some of the more colorful anecdotes, including the precise details of the pistol demonstration, rely on second-hand accounts written down years after the fact, and historians treat them with appropriate caution even while finding them too good not to repeat. Return for a moment to that hut on the shore of Patricia Lake, the brine pipes humming, the gray, slurry freezing layer upon layer in the wooden molds. Nobody working there that winter could have known that the vessel they were building a scale model of would never sail into battle, that the war would be won by aluminum airframes and welded steel hulls rolling off assembly lines rather than by a leviathan of frozen sawdust the length of a small town. But for a handful of months in the darkest period of the Battle of the Atlantic, With shipping disappearing into the ocean faster than it could be replaced, ice and sawdust represented something Britain could not afford to dismiss out of hand, a chance, however strange, at closing a gap that conventional industry could not close fast enough on its own. Project Habakkuk never fired a shot in anger. It never carried a single aircraft into combat. And yet it stands as one of the clearest illustrations of just how close to the edge Britain found itself during the Battle of the Atlantic, a moment so desperate that an oversized block of frozen wood pulp could be discussed in the same rooms as battleships and bombers and taken entirely seriously. The ship, made of ice, was never launched. The crisis that conceived it very nearly sank an empire. In the end, it was not pykrete that saved the Atlantic convoys, but the strange, frozen ambition behind it tells you everything you need to know about how far Britain was prepared to go when the alternative was simply losing the war at sea.